All right. So today we're picking up with 14.6 with bases. I'm going to go back up. This is not working. Here we go. Go back a couple slides just to remind you some of what we did with the acids. So with the calculation for the pH of a weak acid, right? One of the things that we really did here was we set up an icebox. And so largely weak acid and weak base pH questions are going to be equilibrium questions. So we're going to be using iceboxes. So when you have a weak acid, we're generally going to just be calculating the pH because we calculate the concentration of hydronium ion. When it comes to a weak base, we're going to see that we can calculate the hydroxide ion concentration, and then we can get everything else from there. So that's just kind of a quick preview to keep in your mind. But we're going to go through the same processes: writing the balanced chemical equation, making the icebox, making our assumptions, updating that icebox so that when we go to do the calculation, we can plug things in to make it easier, checking our assumptions, and eventually calculating the hydroxide ion concentration, the POH, and the pH at the very end. Okay. Again, if the assumptions don't check out, you're still going to have to do the longer calculations as well. Okay. So let's start out with bases. We've talked about identifying strong acids based on their structures. With bases, it's going to be a little bit different because we just don't have quite the same variety of things for bases. So one of the key things that we have is hydroxides of alkali metals, things like sodium hydroxide or potassium hydroxide, right? The alkali metals are going to be, alkali metal hydroxides are going to be strong bases. The other ones that are strong bases are the three alkaline earth metals seen here: calcium hydroxide, barium hydroxide, and strontium hydroxide. And those are all going to dissociate in water and give you a lot of hydroxide per amount of solute, okay? So generally, sort of like with what we did with the hydronium ion concentration for strong acids, well, for strong bases, the hydroxide concentration is going to be the same as that we did for those calculations. Only here, when we think about something like sodium hydroxide, right, the hydroxide ion concentration will be the same as the concentration of sodium hydroxide, because we know that sodium hydroxide is a strong electrolyte, so it dissociates completely, and we get all of the sodium hydroxide that dissociates gives us hydroxide. If we were to have something like calcium hydroxide, though, right, then the hydroxide concentration will be 2 times, excuse me, I should make that change. Okay, so what we'll say is, for the hydroxide ion concentration of calcium hydroxide, it's going to be twice the concentration of calcium hydroxide because the nature of getting 2 hydroxides per calcium hydroxide, right? And so that's going to be a key here, right? This 2 comes from that 2 there when we're looking at the stoichiometric equivalence, okay? And so hydroxides are basically strong bases. They're ionic substances that have the hydroxide ion. So when you dissolve them, they dissociate, they break apart, they give you that hydroxide ion. Okay. Next, weak bases. So weak bases, you'll see here, we have really two categories that we'll see for weak bases. The first one that we're going to look at is what are called nitrogenous bases, bases that have nitrogen in them. So our example here, this is based on sort of what we kind of briefly talked about before, but bases have either a lone pair of electrons or they're charged, but they need that lone pair of electrons in order to accept a proton. So when we think about something labeled as B with a lone pair of electrons on it, that's really a good example of that is something like ammonia. So ammonia, we know, right, is in H3. And so if we look at some Lewis structure, right? When it comes to nitrogenous bases, there's a lone pair of electrons. If I can change the size of this. Oh, well, I guess I can't change the size of the stylus on here. Hopefully I'll be able to do that when I get the new stylus in. But anyway, you have this lone pair of electrons up here that is where the proton would attach to. Again, so that's why your base is connected to its conjugate acid, where the conjugate acid has a plus charge to it because, oh, it's the neutrally charged base like an ammonia, and when it adds a proton, it becomes a positively charged ammonium. Right? So a big comparison here is for these nitrogenous bases that when you go in and change out, right, instead of having 3 hydrogens attached to the nitrogen, if you change out one of those for a methyl group. So a methyl group is just a CH3. Okay, so this is a methyl, and you'll see more of this when we get into organic chemistry and we do some nomenclature in organic chemistry. But if we look at methylamine, now we're talking about a molecule that looks like this. Right? Still has that lone pair of electrons on there, only now it has this, this methyl group, this CH3. And that CH3 has the effect of essentially donating electron density to the nitrogen, right? It pushes electron density over, if you will, so it pushes electron density to some degree over there, or you can think about it as the nitrogen is pulling those electrons a lot stronger than the carbon is. And so the nice thing about that for the nitrogen is it has stronger electron density on that lone pair of electrons. And if you were to compare the Kb, which we'll look back up at the equation in a minute, the Kb of methylamine as compared to the Kb of ammonia, right? Just changing one of those hydrogens out for a methyl group or a methyl group of atoms, which is that CH3, you increase the Kb significantly, right? In other words, you're going to decrease the pKb. So it becomes a better base because those electrons get shoved over onto that nitrogen, making that nitrogen a little bit more negative, which means it's more receptive to that proton. So when we're looking at a Kb here, right, notice that the Kb, which is based on this equilibrium constant expression in the top right corner, right, that is going to be something that is dealing with the reaction of the base with water, right? So it's reacting with water to form hydroxide. Whereas when we had a Ka, right, the Ka was the acid reacting with water to form hydronium. So this is a different reaction, and that's why it's governed by the Kb, okay? And we'll see the relationship to the Kb in a little bit, okay? So there's methylamine. It's a little bit of a stronger base because it has that electron donating property, which means that the electrons are there's more electron density on the nitrogen, making it more receptive to grabbing onto a proton. If you have ethylamine, it has a similar effect, only it's a little bit greater of an effect. So the hydrogen still attached to the nitrogen. Now, though, it's going to be attached to a CH2CH3, which is an ethyl group. And it still has these the 2 electrons, that lone pair of electrons on nitrogen. And that ethyl group is a little bit more electron donating than the methyl group was. So having an extra CH2 on there makes it so that it's going to be a better base. Not by a lot. You'll notice that 6.3 as compared to 4.4, but they're the same order of magnitude. So they're very close to each other, but still just a slight change makes the difference in the basicity. So you can start to see a trend that when there are more carbons attached to the nitrogen, it becomes more basic. If we now compare this methylamine to dimethylamine, so in other words, we're going to change out the other, one of the other 2 hydrogens. That's a, come on, try to draw this in a little bit better. Okay. Okay, it's apparently as all my stylus is allowing. But if we change out 2 of the hydrogens now from ammonia for methyl groups, right, you get something like that. Now you have 2 things donating electron density. And so if you were to compare those 2, right, you would expect having the 2 methyls, 2 sets of electron donating things, the nitrogen would be even happier to grab onto proton, okay? And if you look at diethylamine, right, so this would be, see if I can just do it this way, CH3, CH2, in CH2, CH, that's really not working right there. The challenges of online education. All right, try this again. Hey, I made it, okay. So we've got our lone pair of electrons, a hydrogen. So as you can see here, even if you compare those 2, right, the one with the more ethyl groups is going to have a larger Kb, smaller pKb, essentially be more basic, okay? So that's the trends for the nitrogenous bases that we'll encounter.
I have a question, sorry, about like what is it about the hydrocarbon that donates electron density to the nitrogen?
Yeah, so you have these protons on the carbon, right? And so those are, the protons have a lower electronegativity than the carbon does. And so the carbon's grabbing onto some electron density from that, which in the bond with nitrogen, right? If you think about it as electrons are being pulled from the hydrogens over to the carbons, which means the carbons have more electrons in the bond with the nitrogen. And so they give up their electrons a little bit easier, basically. So it's all sort of a connectivity of electronegativity, right? Which way, the secret to organic chemistry, so if I talk about the secret to general chemistry, chemistry overall, is charges. The secret to organic chemistry is electronegativities, which is based on charges, right? But it's a matter similar to the inductive effect that we talked about when we looked at the strength of acids, right? The more that the oxygen pulls the electrons away, the stronger the acid, right? Whereas the more, in this case, the more that carbons you have, the more electrons are going to be going over to the nitrogen, the stronger the base. Okay?
Okay, thank you.
All right, so the other category of weak bases is really just the conjugate bases of weak acids, right? We know that weak acid only dissociates a little bit. But if you have a deprotonated weak acid, something like, as you can see here, something like fluoride or acetate or bicarbonate or carbonate. I'm missing a 2 on there. Hold on a second. Make a quick correction in this. One second, I'm going to bring that back up in a second. I noticed I'm missing part of a charge. Aha. There we go. So let's go back to that. Oops. Okay, give me one moment. Oops. Aha. Make sure we can talk about this properly. Okay. First time using these slides, so there's always going to be some sort of an error here. Okay. So on this one, it didn't come. Oh, I put it in the wrong spot. Stop that again. How about there? Pay attention to what I'm doing. There we go. Okay. So on this, what you can see is whether it's bicarbonate, which is the conjugate base of a weak acid carbonate, or whether it's carbonate, which is the conjugate base of bicarbonate, or dihydrogen phosphate, hydrogen phosphate, or phosphate. These are all examples of weak bases, and you can see the KBs right here. They're small, right? They're 10 to the minus 2, 10 to the minus 11. They're small values. Now, the way you would get one of these into solution is actually not trivial, right? Well, it's easy to do, but it's something we need to make sure we understand, okay? Now, before I go into how to do that, I want to highlight the idea now when we look at the base of the Kb of a conjugate base reacting with water, right? That conjugate base is, notice it's that charged substance, that negatively charged substance reacting with water to form the protonated version or the conjugate acid and hydroxide, right? So you're still looking at hydroxide as being part of this Kb equation here. Now, the way you get something like B minus into solution, we'll use an example for fluoride. If you were to have sodium fluoride, we could consider that aqueous because it'll dissolve because it's an ionic substance and it breaks apart, as we know, into its ions. And we know that ionic substances dissociate if they are an ionic substance that has an alkali metal as the cation. We consider them to dissociate completely, right? So we have sodium ion and fluoride ion, okay? And it dissociates completely. Now, another thing about this is, and something we'll look into more, is the effect of pH on or from ions themselves. So this is where we're going to explore this more when we get to 14.8, right? Is we're going to say, okay, well, how do these ions differ in how they affect the pH of a solution? For now, I'm going to tell you that the sodium is not going to have an effect on the pH, and we'll talk about why that is more when we get to 14.8. But for us, the fluoride is the important thing. So if we can get fluoride into solution, that's going to be an important thing for calculating the pH of a weak base that has fluoride in it, right? A weak base solution that has fluoride. So we're going to start out, we're going to do some calculations of some strong bases in water, and then we'll do some weak base calculations. So the first calculation is calculating the pH of a 0.0132 molar sodium hydroxide solution. Now, this is asking for pH, but we don't calculate pH directly from a base being dissolved. What we calculate more readily is the pOH. So we know that our concentration of hydroxide is going to be the same as the concentration of sodium hydroxide, right? And so what we can do now is we can say, well, the pOH will equal negative log of the concentration of the sodium hydroxide. In a similar way to calculating pH from a strong acid was just the negative log of the concentration of the strong acid. So now you can say pOH is equal to negative log of 0.0132 molar, right? And so that will give you a pH, or pOH, excuse me, of 1.879. Okay, and you know it's 1.879. You have 3 sig figs there in that value, which means 3 significant figures after the decimal place in that pOH value. And then to calculate the pH, you can say, well, 14 minus 1.879 gives you 12.121, right? Would be your pH. Of course, the other way you could do this, right, is if you wanted to find the concentration of hydronium ion. So there are multiple ways of doing it, and we know the concentration of hydronium ion is Kw divided by the hydroxide ion concentration, which is the same as 10 to the minus 14 divided by the hydroxide ion concentration, in this case, 0.0132. And so you do that, and you get a value of 7.57 times 10, 7 times 10 to the minus 13. And if you now take pH will equal negative log of 7.57 times 10 to the minus 13. And you get same value. Okay? And so you can calculate the pH after you get the pOH. Okay. Come on. Why? So, okay, so the reason why you have 5 sig figs in the pH goes back to, I know this is like way back, it's day 1 of Chem 102. So the number of significant figures, right, in the value here is going to equal the number of significant figures after the decimal place in the mantissa of that value. Okay, that's where you get, it's not that it has 5 sig figs, it's that there are 3 sig figs after the decimal place. The characteristic, right, so the characteristic is this part, that's tied in sort of magnitude wise in a large way to the power of 10 in the parentheses there that you're taking the log of. And so there's more on this stuff in Appendix A if you want to go and review it a little bit more. All right, I'll switch up colors, make it a little bit more fun. Here we go. Okay. Come on. One sec. All right. So next thing, if we were to calculate the pH of a 0.00247 molar barium hydroxide solution, so this is where we need to account for the fact that barium hydroxide has, right, 2 hydroxides for every 1 barium hydroxide. So the concentration of hydroxide will be equal to 2 times the concentration of barium hydroxide. And so you'll get 0.00494 molar for that concentration. And then from there, it's just a matter of doing the same process, right? You can do it either the first way, where you find the pOH is equal to negative log of 0.00494, or in this case, 2.00, sorry, that's not right. Looking at the wrong value. Excuse me a second. There. 2.306. We can clean this up a little bit for you. There, 2.306, and then find pOH, or excuse me, pH is equal to 14 minus 2.306. So you wind up with 11.694. Or you could do it the other way, where you calculate the hydronium ion concentration. So 10 to the minus 14 for kW divided by 0.00494 gives you a value of 2.02 times 10 to the minus 12 molar. Right, and so you take pH equals negative log of 2.02 times 10 to the minus 12. And so you wind up with a pH of 11.694. So you can do it either way. It just sort of depends upon what you're more comfortable with, and that should be fine. Okay. So any questions on calculations of pH of strong base solutions? Remember, and by the way, notice these strong base solutions have fairly large concentration of hydroxide compared to the concentration of hydroxide from the autoionization of water. So you can look at it as this way. This works for the concentration of hydroxide from the base that is much greater than the concentration of hydroxide from the autoionization of water, right? Similar to what we did with the weak acid calculations and the concentration of hydroxide, or excuse me, the concentration of hydronium from the strong acid. If the concentration of the strong acid was like less than 10 to the minus 6, then you had to take into account the concentration of hydronium from the autoionization of water. Same idea goes here, but for hydroxide instead. Okay, so we'll do an example of a weak base in water. And so this one here, we've got a solution of, and this will be our last example, by the way, and then we'll take we'll stop there and move on to lab stuff. So our last example, weak base, the weak base being ammonia, okay? And so here, this is really similar to the weak acid calculation, okay? So the first thing we should always do is write out that the chemical equation and along with that, the Kb and the icebox. So here we can say ammonia plus water reacts to form ammonium plus hydroxide. Okay, and so here's our chemical equation. I'm going to actually do my icebox right below it. And I'll put my Kb equation just down off and off to one side. Okay. So Kb should equal the concentration of ammonium times the concentration of hydroxide over the concentration of ammonia. Right? And so we know that that is equal to, of course, 1.8 times 10 to the minus 5. So here, we're also going to make some assumptions. One of the things I'm doing, again, is whenever you see water in these ice boxes, just dash it out, make sure it's not part of it, just to remind yourself that it doesn't go in that Kb equation. The next thing is I want to write the assumptions in before I start filling in the ice box. Okay, so the assumptions that we're going to make are, again, the concentration of hydroxide from the autoionization of water is much less than the concentration of hydroxide that we get from the ammonia reacting with the water, right? Now, this is a pretty good assumption because if you look at the concentration up here of the ammonia solution, that's a pretty big concentration, right? 0.15 molar. Even if you take 1% of that as dissociating, then you're gonna get a value that you can exclude the initial amount of ammonia or of hydroxide. So with that assumption, we can go up there and put a 0 with the hydroxide. The other one is that the concentration. Excuse me, actually, I'll just write it in as the 5% rule, and we'll talk about it just briefly again. Really there. So the 5% rule, which states that, well, if we know the initial concentration of ammonia as 0.1500, and we know that for every ammonia that reacts, we lose some amount of it, then we know our equilibrium constant of ammonia is, the equilibrium concentration of ammonia is 0.1500 minus X, And here we can basically, the 5% rule says, well, X is so small that we just get rid of it, okay? Just as a reminder of what that one is. Then over here, for the initial concentration of ammonium, it's 0 because none of it's reacted. But for every ammonia that reacts, we get plus some amount of ammonium and plus some amount of hydroxide, such that we have X and X at equilibrium, okay? And so we'll continue this on to the next page. I'll give you a second if you want to take a picture of it or whatnot, or if you need me to go back at some point, let me know and I'll be happy to go back. But we can do the calculation for the hydroxide ion concentration, right? Because that's the next thing we're going to want to do is the hydroxide ion concentration calculation, okay? So that's our next step. So what we do here is we take our Kb, which is 1.8 times 10 to the minus 5. And this value, this 1.8 times 10 to the minus 5 here, that value is actually, that has significant figures to it. It's actually, you can get a better value and we'll see better values when we look at some tables in the future. So 1.8 times 10 to the minus 5. So that's our significant figure limiting value in this case, is equal to X squared over 0.1500. And so here we can say that X squared is equal to 2.7 times 10 to the minus 6. And so X will equal to the square root of 2.7 times 10 to the minus 6, which will give us 1.64 times 10 to the minus 3. With, of course, significant figures to the second point there. And so that we know because X up here, right, X is our hydroxide ion concentration at equilibrium. We can now say that this is our concentration of hydroxide. Okay. And then from there, before we actually go calculate, we want to check our assumptions. And so to check the 5% rule, actually, we'll do the autoionization of water first. So 1 times 10 to the minus 7 molar from the autoionization of water divided by 1.64 times 10 to the minus 3 times 100% is equal to 6.1 times 10 to the minus 3%. Right? And so that checks out. The 5% rule is the other one, right? And so 5% rule tells us that that 1.64 times 10 to the minus 3 over the initial concentration, that's a 6 there, over the initial concentration of 0.1500 times 100% is equal to 1.1%, right? And so that 1.1% is less than 5%, therefore that checks out also. And we can go and figure out the POH, right? Negative log of 1.64 times 10 to the minus 3, which gives us a POH of 2.785, where we have significant figures to the second place after the decimal. That's not right. We have three, because we have 2 sig figs there. And so 2 sig figs there mean we have 2 sig figs after the decimal. And so our pH equals 14 minus 2.785. And so we wind up with 11.21, right, as our pH, okay? And so with that, we'll stop for the day with examples, but we've gone through a couple of calculations, right? The strong base with sodium hydroxide where there's one hydroxide, a strong base with barium hydroxide where there are two hydroxides per mole of barium hydroxide, and then we've done a weak acid, excuse me, a weak base of ammonia. Okay. What we'll do next time is we'll look at a weak base that's the conjugate base of a weak acid. Okay. And so with that, we'll call our lecture for the day, and we'll take a second if I can answer any questions that you have, and then we'll go on and do some lab stuff.
When you were checking the assumptions for the 6.1 times 10 to the negative 3, can you verify what you were doing there? Or clarify?
Yeah, so on that one, let me go reshare that screen. Okay. So this one right here, you mean, right? Hold on. Make sure I've got this.
Yeah, the 1 times 10 to the negative 7 over.
Yeah, so that's that right there. Here, I'll redo this whole thing. Right. So what that one is, so we'll do this. Let's hold on. Keep those. We go find that page again. Oop. Okay, I'm gonna go find that page again, and I'm gonna add a page to it so that we can go through those checking of assumptions again. Blank page, perfect. Okay, so we'll do that. Go back and share this again. There. Okay, so we were on this page. Come on. Why is my computer not working? Okay, there we go. So we were on this page. So I'm going to take this right here. Oh, come on. Okay, so I'm going to take this right here, and we'll go to the next page and we'll look at the checking assumptions. So we have two assumptions to check. The first assumption to check is that the concentration of hydroxide from the autoionization of water has to be much less than the concentration of hydroxide from the base. Okay, that's the first one. And so this assumption says that, well, the concentration of hydroxide from the autoionization of water, which is 1 times 10 to the minus 7. Okay, so that's what this piece here goes there on top in the numerator. That is divided by, our value was 1.64 times 10 to the minus 3 molar from our calculation. Okay, that value comes from this concentration that we calculated for the hydroxide ion concentration. You take that, multiply it by 100%, right? If that value, which in this case comes out to be, where did I have that? There it is, 6.1 times 10 to the minus 3%. Right? If that value is less than 5%, right? Really, that's good. That checks out okay. You're fine. Okay?
Okay, thank you.
You have to go back and do that again. That work for you?
Yeah, thank you.
Okay, great. And then the other assumption you have to check was the other one was the 5% rule. Okay. All right.
I have a question about sig figs. Why did the sig fig go from 2 to 3 after we took the square root of x?
After we took the square root of x, up there?
Of x squared, sorry.
It didn't. See this? See that my line right there?
Yeah.
That line is saying that that's the last significant digit.
Oh, okay. But then that's still carried along?
Yeah, so like in the calculations after that, when you're doing the assumption check, you don't really care, right? Because all you're checking is to see if it's less than 5%. But you'll notice I underlined that there too, right down here. Right?
Mm-hmm.
And that translates into having a significant digit to there, which translates into the significant digit here.
Okay.
I know it's
Okay,
hard
thank
to
you.
check when I don't have a board in front of me to point to those things. But that's really what we're looking at.
Okay, thank you.
Mm-hmm. So in other words, it doesn't. So you're right. Okay. Any others?
What do we do if the autoionization is greater than 5%?
Yeah, so what you do in that case is you go back and redo your ice table. And so if the autoionization of water is greater than 5%, then what you do is you go over here to the ice table, and instead of having 0 here, you would have to change that to 1 times 10 to the minus 7, which means that that value would be 1 times 10 to the minus 7 plus x. And then your math just gets a little bit more complicated. Okay.
Oh, why didn't we set 1.8 times 10 to the 5th equal to x squared?
So here's your KB, right?
Mm-hmm.
KB, right, is 1.8 times 10 to the minus 5, as you can see from there, right?
Mm-hmm.
So that's x, right, at equilibrium, right? That's your there at equilibrium, right? Also the hydroxide ion.
Oh, yes. Okay.
Got it?
Yeah.
Man, this stuff is so much easier on a board when we can see it.
Yeah, I see it now. Sorry.
Great. All right. Any others?
I was just wondering if you could go back to where the pH was. I didn't get to write that down.
Sure. That one. Yeah, your pH right down there. And I will post these slides a little bit later, right, with all the annotations in there. And what I will do is I'm going to stop the recording now, assuming I can.